Alrighty. Well, again, happy Halloween Eve to everyone. I suppose that's what it is. The second spookiest night of the year. So, want to start here, just do a little bit of review of what we've seen before with sorting, and then talk about a new fancy sorting algorithm called QuickSort. So it's been a little bit, but so far we've seen two different ways, primarily, of sorting something. So the first being insertion sort and bubble sort. So both of these are sorting algorithms that make a lot of sense when you think about it, especially insertion sort. So remembering that insertion sort works by, in the not in place way, you keep a separate list down here. You have your list of elements here that are not sorted. And as you go through your list here, you look for the right spot in this list. And then you just keep adding the elements that you find here to the right place inside this other smaller array. This process of finding the right spot is also kind of a long process. For every element, you might have to look at every other element. So this is a quadratic sort for insertion sort. So it makes a lot of sense though. Like if I gave you like a list of like 15 cards with different numbers on them and told you to put them in order, you would probably do something like this. Or maybe you do something where you'd like look through this for the smallest thing and find the one and then put that aside. And then look through this for the next smallest thing and then put that aside. That'd be another quadratic sort, right? Because you'd have to like look through this to find the smallest thing over and over and over again until you got rid of everything. So that's basically what insertion sort does. Bubble sort is another way of implementing a quadratic sort, which says, instead of building some new thing and trying to shuffle stuff around, let's do basically the minimum finding version, where just look at every two elements, see if they're in order, and if they're not, then swap them. Then keep repeating that process until the bigger elements bubble up to the top. And this one we finished right away at the first pass, but if this last number was really small, then we'd have to do a pass. We'd get to the end, and then we'd swap these. Then we'd have to do another pass, and then swap these. And then we'd have to do another pass, and then swap these. Then we'd have to do another pass and swap these. It's a very long, arduous process before we finally end up getting the smallest thing back. So they're very efficient in terms of understanding, but they're not very efficient in terms of runtime efficiency. It's another quadratic algorithm. So, what we're going to look at is, in the same vein of continuing on things that you should know about, but people probably won't ask you to make, is how can we come up with a way of taking a list of numbers, anything that we can arrange, and find a way of putting it in order faster than having to look at a quadratic time, which means something faster than, for every element, you might have to compare with every other element. Because there is a way to do it faster, but it's a little bit tricky to look at. So there are two main algorithms that we talk about that are faster than quadratic. Those two are QuickSort and MergeSort. Today we'll be going over QuickSort and figure out how is it possible to be sorting something more efficiently than what insertion sort and bubble sort are doing. Because remember when we looked and saw the run times of those, like in the playground, once we had like 1,000 things we're trying to put in order, it took forever. Because if it's quadratic, it means you've got 1,000 things that have to look at 1,000 things for each of them. That's 1,000,000 things. And 1,000,000 operations takes a long time. So on playgrounds, like the number here when you're running something counting up, takes a long time for it to get to 1,000,000, right? So it's a very slow procedure about sorting large amounts of things. So this is going to be faster. How? We'll find out. To intro it, we'll take another quick look at our sounds of sorting here. So this is just the same thing we saw before. Let's see what it's doing, and then we'll try to understand what the algorithm looks like. Because it's a little bit complicated, but it makes a lot of sense once you start going through it. So we're going to try this with, it's here somewhere. Actually, where is it? Did I get rid of it? Am I just blind? QuickSort? There it is. That makes more sense. We're hearing nice sounds. We see that things are moving around, but we're not maybe exactly sure how it's moving. We see that one of the things is like off to the side, like picking up something. And you see that we've made like the left side and the right side, they're both like kind of sorted. And then we're tackling each of those in order. It's very nice sounding. So it's like now we have our left side sorted, but our right side not sorted at all. That's kind of weird. We're pulling this thing up and then we're shifting a bunch of stuff around. And then after all that said and done, we end up with something sorted. Okay.
Sorry, I just need my computer.
Oh my god!
You should split up to look for clues.
Oh, thank you.
Cheekies indeed. I wish I could give you advice if that happens in an interview, but I've never had that happen before. You just gotta roll with the punches. Anyhow, this is doing a bunch of random stuff. We're not exactly sure what's happening yet, but we might have noticed a couple things. First, it looked like we did the left side first before doing the right side, which is interesting. And then second, we saw that it was pulling one of them down and then comparing a bunch of stuff with it, and then shifting stuff around. So we could look at another visualization just to get a sense of what it is before we talk about it in a little more detail. This is with a much larger set here. It sounds a lot weirder. This one's very dissonant and strange sounding. But you can see we pick something in the middle and we end up shifting a bunch of stuff relative to it. And we get these weird gradations of stuff that are kind of sorted relative to each other. And then we do a bunch of cleanup on each of those sections to be repeating that process. It's a very weird looking algorithm, right? Like, this made sense for bubble sort. You're just like, all right, just swap a bunch of stuff. Like, just looking at this, if you were like I was, you have no idea what this is doing to actually sort something. You're like, well, it sorted it, I guess. We kept shifting stuff around and we ended up like making 3 different piles of stuff. But what's it actually doing in order to sort something? So we're going to be looking at a more simplified version of this algorithm here because it's more important that you understand conceptually what this is doing to sort something without actually going through the full implementation. Now, QuickSort is also the actual algorithm that is used when you type in like r.sort. This is the algorithm that Swift uses to actually sort it. Unless the array is very small. If there are 10 elements or less in it, it actually uses insertion sort. It's kind of interesting. So you already know insertion sort. So if you're sorting a very small array with like only 6 or 7 elements, it's probably just using insertion sort. So you already know that one. So you're already ported away to understanding what is Swift doing to sort things. This is the main part. This is what it's running for big collections of stuff that you want to put in order. So, what is this algorithm actually doing, aside from those confusing pictures? The pictures make it look a lot more confusing, but conceptually, it's a fairly clean way of thinking about how we want to do it. So the main idea, and hopefully we got a hint of that in this here, is this is a divide and conquer algorithm. We pick a rule, we end up splitting some stuff so that we got a bunch of smaller stuff on the left, and we got stuff that's all bigger on the right, and then we kind of repeat that process. We do that again for the smaller stuff, and now we have even smaller stuff on the left, and bigger stuff on the right that's still smaller than this stuff. And we repeat that, and we repeat that, and we keep repeating it until our stuff is sorted. We're only looking at one thing at a time. When you have an algorithm that makes sense by saying, we're going to do this, split it in half, and then we're going to do the same thing for the left half, we're going to split that in half, we're going to do something to that, we're going to keep splitting in half over and over again, and keep applying something to it, We call that a divide and conquer algorithm. And it's also a good candidate for a recursive algorithm. Something that you're saying, we're going to apply some process that splits this into a couple pieces. And then for each of those pieces, we're going to apply some process that splits that. And then for each of those pieces, we're going to apply a process that splits them again. We're building a recursive process to try to figure this out. So what are we actually doing? What does this look like? So taking a look at an example of like a particular array. So let's say that we have an array, let's say here, great, 11, 8, 15, 11, 8, 15, 10, 4, 14, 2. All right. Here's QuickSort. The idea is you pick a value arbitrarily and call that your pivot. That was the green line you saw in the video we just saw, or that was the pulled aside like bar, music bar we saw in the one before. Then you compare everything to that pivot, and you split this into 3 separate arrays. An array of stuff smaller than the pivot, an array of stuff that's the same as the pivot, and an array of stuff that's bigger than the pivot. Then repeat this process until you have a bunch of arrays that only have one thing in them, and then just smash them all together. Let's take a look at what that actually looks like in practice. Here's our original array. We can pick whatever pivot we wanted, whatever comparison point that we're using to split left and right. For simplicity here, let's just pick the middle one. Talk a little more about pivots later, but let's just pick that one. So we say that 10 is going to be our pivot. We're going to then go through this array and build 3 arrays. One with everything smaller than 10, one with everything equal to 10, and one with everything greater than 10. So we do that, and we say we've got 3 arrays here. 11 is bigger than 10, so it goes here. 8 is smaller than 10, so it goes here. 15 is bigger than 10, so it goes here. 10 is equal to 10, so it goes here. 4 is smaller than 10, so it goes here. 14 is bigger than 10, so it goes here. And 2 is smaller than 10, so it goes here. So we split this into 3 arrays that are still not sorted. 8, 4, 2 is sorted the wrong way, and 11, 15, 14 isn't sorted at all. But it's a little closer, at least, right? Everything here is smaller than this stuff here. So it's better, but not quite where we want it to be. So what do? We do this same process on each of these smaller pieces. So we say, take this array, pick our pivot in the middle as 4, and then we build 3 arrays. We have an array of stuff that's smaller, stuff that's equal, stuff that's bigger. We see an 8 that's bigger than 4. We see a 4 that's equal to 4. We see a 2 that's smaller than 4. Then, each of these only have one element in them, so we smash them together. So the last step of our process is, if there's only one thing, an array with one thing is always sorted. Right? If I tell you to sort an array and only has one value in it, it's sorted. Can't do anything else to it. So then, we end up with 2, 4, 8 as this sorted version here. Our 10 is already sorted, because there's only one thing in it. We apply the same thing to this side. Here, our pivot happens to be 15. So we've got our smaller, our equal to, and our bigger. 11 is smaller than 15. 15 is equal to 15. And 14 is also smaller than 15. We know that the 15 here is already sorted, but we don't know that these are necessarily sorted. So we have to run QuickSort again on this last bit here. We pick our pivot arbitrarily, say 11. We build our array of stuff that's smaller than 11, nothing. Stuff that's equal to 11, 11. And stuff that's bigger than 11, 14. So this turns into 11, 14. This here turns into 15. Now all of these bits are sorted here, and I just smash them all together. 2, 4, 8, 10, 11, 14, 15. By going through this process here, I have taken this original array, split it, each time splitting it into stuff smaller than some midpoint, stuff equal to some midpoint, stuff bigger than some midpoint, and repeated that process until I ended up with each of these splits ending with one single array. Here, 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 of my all single arrays here. Once I have those single arrays, I smash all of them together. So I know that each one of these is in order relative to where they should be in the array. Yeah?
So if you have an array of 1,000,
Yep.
that's equation array for each individual integer.
So the algorithm that we'll be going through is not a very efficient algorithm in terms of space complexity because we're building a lot of arrays, right? You're exactly right. There is a way of doing this here that doesn't require building these arrays. Conceptually, all you would need to be doing is say, instead of making 3 arrays, let's just shuffle stuff around in this array, kind of like bubble sort, so that we make sure that we have our pivot and everything to the left of it's smaller and everything to the right of it's bigger. That's how it's actually implemented. We're going to focus on the array space complexity not great method because it still gets the point across. And I would be surprised if an interviewer is asking you about, these are called partitioning schemes. I'll talk a little about it, we'll go through like the Wikipedia stuff on it, but that's a little more than someone might expect you to know if they're just trying to make sure that you have a knowledge of sorting algorithms. So let's say we've done this process here, right? We end up with each of these single arrays, like so, and then we just smash them all together to get this. This looks like it's better than quadratic time. But what is actually the runtime of this algorithm that we've described here? So we know it's going to be probably worse than linear, since we still have to look at everything at once, right? We had to look at everything in this row to figure out where it fit here. Then we had to look at everything again. Then we had to look at everything again. Then we had to look at everything again. So it's worse than linear, because you have to look at everything more than once. And it depends on how much stuff we have, for how many times we have to look at it. But it's better than quadratic, because I get to do all these cuts in half a lot. Yeah. Yeah, so it's what we call linear rhythmic. Yeah, logarithmic is that log of n part. If it was just logarithmic, you'd win like a Nobel Prize for finding like a logarithmic sorting algorithm. That'd be great. Sort something without looking at every element in it would be incredible. But it's a little bit slower. It's linear rhythmic. Why? Because each of these passes here, we have to look at n things. Right? We had to look at each of these elements to figure out which of these buckets to put it in. Then we had to look at these things here to figure out which bucket to put it in. We had to look at this and look at these things. We had to look at n things again and again. But how many times did we have to do that? What's the height of this here that we've drawn out? Well, it's a bunch of cutting in half periods, right? And we use logarithmic to explain what time looks like when we cut something in half a lot. So if we started with 1,000 things in it, there'd be 1,000 elements here on average, and then 500, 500. 499, 1, 500, whatever it is. 1,000, then 500, 500. Then 250, 250, 250. Then 125, then whatever half of 125 is, 70 something. Then, not 70 something, 60 something. Then 60.5. Then 31 point whatever. Then we keep going down. But we don't have 1,000 rows down. We only have log base 2 of 1,000. Log base 2 of 1,000 is, 10, 28's our next power of 2? So that's like 8 or something? It's not big. Log base 2 of 1,000. Nope. So log base 2 of 1,000 asks the question, if I started with 1,000 things, and I kept dividing by 2 a lot, what do I end up with? And this is here a little more than 9, somewhere between 9 and 10 times, to go from 1,000 things all the way down to 1 thing. So we don't have to go down that far. We have to go across 1,000 every time that we're looking at an array, but we'll only have to do that process 8 or 9 times, which is pretty efficient. So the width of this here is n, and the height of this here is log base 2 of n. If there's anything to know about quicksort or about these faster algorithms, it's a conceptual understanding of this picture and why it gives that runtime. There's a better drawn link to that at the bottom of the lesson. Better drawn because I didn't make it. So this is conceptually the same image here that explains why the runtime is what it is. I'll spend a little more time on this picture because this is the real meat conceptually of what is quicksort. If someone's asking you in an interview, like, hey, you used this dot sort here, how long did it take? You should have memorized that it is n log n. So anytime you say r dot sort in a solution to a whiteboarding question, and someone says, how long does it take to do this? You should know sorting takes linear rhythmic time, n log n. So step 1 is just make sure that you have that memorized. Sorting is better than linear, but worse than, better than quadratic, but worse than linear. Better would be to have a brief conceptual understanding that, well, it's better than quadratic because we don't have to do the for everything, look at every other thing. But it's worse than linear because we've got to look at everything more than once. And the number of times we need to look at it is log of n, where n is how much stuff we have in our array. That's how much duplicate looks we have to make at every element. So we have this 11. We look at this 11 here 1, 2, 3 times, I guess 4 times before we end up finishing here. And our array has 1, 2, 3, 4, 5, 6, 7, 8 elements in it, which is 2 to the 4th. So that's why, so you can tell how many times do I need to look at any individual one of these based on the size of it. And that's logarithmic for how many times you need to look at it, and you have to look at each of n things log of n times, which means that your total runtime is n log n. So this picture is the most important part about these faster sorting algorithms. And this is how it can accomplish that kind of magic of how are we able to take a list of things and sort it better than insertion sort and better than bubble sort? It has to do with dividing in half a lot. So any algorithm that's going to be a better sorting algorithm is going to have that element of, well, we're still going to need to look at every element at least once. But we're going to do better to control how many times you look at it by trying to cut it in half over and over again. Now, I want to talk a little more about this pivot picking here that we're doing. So I just kind of declared arbitrarily that we would pick the middle as the pivot for breaking off our left, our middle, and our right. And that worked pretty well with what we had here, right? We picked this middle, and then we split up into something that had 3 things, something that had 1 thing, and something that had 3 things. That was pretty good. We really want it to be a splitting in half over and over and over again. But something to be careful about is if your pivot is bad, this sorting algorithm becomes no better than bubble sort. What does that look like? Let's say that I have a bad pivot that I'm picking for the same array. I'm going to sort the same array, but I'm going to have a different method for picking what my pivot is for it. 10, 4, 14, 2. Let's say instead of taking the thing in the middle, I want to take the thing at the end. I mean, why not? Right? I have no idea how this thing is organized, so I'm just picking something arbitrarily. So instead of picking my pivot at the middle, I'm going to pick the end, and we'll see what happens. Now when I'm going through, I'm going to be building an array of things smaller than 2, an array of things equal to 2, an array of things greater than 2. Well, nothing here is smaller than 2. So as I go through, I'm going to end up putting every element in this array here except for the 2, into the right part of things that are bigger than 2. Well, that's not great, because now our cut doesn't look very good. We want to be splitting in half every time to get this logarithmic structure. If I'm cutting like this, it's going to take a long time because I only got rid of one thing from this array. Instead of getting rid of half of the stuff from it, I only got rid of one thing. So that's definitely not very efficient. And if I repeat this here, picking the rightmost element, my 14 is also not a great pivot, it so happens. Because my 14 only has one thing that's bigger there. So I end up with 11, 8, 10, 4, all in the same array. So this is also not a great pivot, right? I wanted to split by getting rid of half of my stuff. I only got rid of 2 things. That wasn't great. And here, my 4 pivot will also have the same problem. I'm going to end up cutting this here into an array of stuff that's smaller than 4, nothing, an array of stuff that's 4, an array of stuff that's bigger than 4, which is the rest of my array here. So we'll still end up sorting it, don't worry, but this is a much longer process to be going through and sorting here. I had much worse cuts that I was making in my sorting process. This pivot then is a little better at least, because then I get my 8, 10, and 11 structure, 14. So because we only have 8 elements, or 7 elements in our array, we don't have that many more steps, but this was basically done after 3 cuts. This one took 1 extra one to do it. Now, we didn't have that many elements, but you can see if you had 1,000 elements, and instead of splitting 500, 500, you split 1, 999, and then you take that 999, you split 1, 998, and you keep splitting like that, you don't get a log n height at all. Instead, if you took something like 1,000 cuts to 1, 999, that cuts to 1, 998, that cuts to 1, 997, and so on, the height of this would be n. So if your pivot is bad, the runtime of this goes from linear-arithmic and log n to quadratic, where you have to take one thing out at a time and keep going. Now, you shouldn't need to worry too much about actually making a pivot. It's just a potential downside. It's if you get unlucky, this could actually run a little bit slower. In order to try to alleviate that, you could try to be a little bit smarter about how you're picking your pivot. For example, instead of just picking the thing in the middle or the thing at the end, you could sample like 3 or 4 values at random, average them, and then use that as your pivot. So that might be a smarter way to do it. That would take a little bit more time, since picking a pivot means you have to look at 3 or 4 things and do an operation, but would mean that you're less likely to run into a situation where you happen to pick all of the 3 smallest things, and then you get a really bad cut that way. So that's a conceptual idea of how this algorithm works. We're going to go ahead now and translate that into actual code, and then we'll get to see how fast this is in comparison with some of the other sorting algorithms that we've seen before.
Why does dot sort use insertion for under 10 elements?
That's a good question. So because big O notation only matters with large amounts of elements. So this process with only 8 things in it is actually not that efficient. We have to spend a bunch of time doing stuff, and like the startup and ramp up time to do a bunch of these comparisons might be longer than the way that insertion sort is doing it. So big O notation only matters when you're talking about hundreds or thousands of elements. If you're talking about 10 things, big O does not matter. And so you can use this to your advantage to demonstrate your understanding. Like, let's say that you have something that is going to run for every letter of the alphabet. There's only 26 letters. Big O doesn't matter for that. If you wanted to scale it to other fictional alphabets that might be thousands of letters long, then you would care. But the reason they use insertion sort is because big O does not matter for 10 elements. So they pick that as the line that they say, well, we know that worst case scenario, we're doing 1,000 operations, whatever. That's still, for whatever reason, space, memory, the amount of time it takes to do those operations ends up being more efficient. It might be because this is recursive, and maintaining that recursive structure might be a little more complex, more complexity. I'm not sure the actual technical specifics of it. I bet there's an explanation on the sorting thing, so if anyone finds that out, I'll check afterwards. I'll get back to you with more information about like specifically what is the technical limitation of it. But I know what's powering that is that big O does not matter for small amounts of elements. Yeah.
So like in an interview, they're like sort this array of 10 items. Would it make more sense for us to say, well, I'm going to do this insertion instead?
So.
Sort of trying to be like fancy and show off that you know it is.
So it is rare that someone would actually ask you straight up, build an algorithm to sort 10 elements. That's a little unusual. This would be in the context of, they might ask a question that you could sort as part of your solution and use the built-in sort. So for example, let's say, we've asked this before, right? Write an algorithm to find the second smallest element in an array, right? One solution to that is sort it and then give me the second thing, right? That's a slower solution than iterate over the array, track the smallest, track the second smallest for every new value you find, check if it's smaller than the smallest, and then overwrite it, and change the second, blah, blah, blah. That's still a faster algorithm because sorting takes linear rhythmic time. So that's more of the like questions that they would be getting at. If they are asking you about quicksort specifically, it would just be about like conceptual understanding. Maybe they might actually ask you to write it, but I wouldn't. So the better way to put it is before you ever try to implement anything of a sorting algorithm, just ask, can I use the built-in sorting algorithm? 99% of the time they'll say yes, but they might ask, but how long will it take? And then you should just know sorting is at log n time. Yeah. The 10 elements or less insertion sort thing is more of a bit of trivia. I wouldn't be surprised if most interviewers didn't know that. Yeah. So like they're probably not going to ask you because they probably just don't know. That's just the specifics of the language kind of thing. Okay, so let's say that we're building our own quicksort here. So we're going to make our function, which we'll call quicksorted. We're going to make it nicely genericized. So it's going to have some comparable generic thing that we're putting inside of it. Our function here is going to have an input of some original array, which is the same generic T. And it's going to want to take in a closure that says, how do I know if it's sorted or not? So we're going to have our isSorted closure, the type of which is something that takes in 2 of these elements and returns a bool. And this whole thing returns a sorted array of our generic keys. I'm going to pause for a second just on the function declaration. I know we've seen it before, but it's really important to have an understanding of like, this is a really weird type, right? Like, this is a type in the same way that an integer is a type, in the same way that a string is a type. The highlighted section is a type. It's a closure, and it's a closure that has the signature of taking in 2 generic T comparable things as inputs and giving you a bool. The reason we're asking for this is because we want more information about how we should do something as a function. So remember, way back in Unit 1, we use closures when we want more information about how we should do something. Map takes a closure because it says, how should we be mapping these? Reduce takes a closure because it's, how should we be smashing these things together? Our sort takes a closure because it says, how should we be arranging these things? What's greater than something else? We could just make this like an enum and just say like ascending, descending, but this lets for more freedom for the end user to be specifying how they want the different elements to be sorted relative to each other. So make sure that you, if you're not comfortable or familiar, like understanding what this is doing in the function, make sure to review some of the closure stuff that this becomes a little more familiar, that this is an argument to a function and it is a, what I think Swift calls a first order citizen A closure here as a type is a type that is just as valid as any other type in the Swift language. Like you can make an array of ints, totally fine. You can also make an array of closures that take in 2 ints and return a bool. Yeah, thank you. So like both of these are equally valid Swift lines here on 11 and 12. Like int is a type and a closure that takes in 2 ints and returns a bool is a type. It's rare that you would want to build that array, but you could if you wanted to. So closures are first order citizens. That's why they get to be types into methods like we see here. Okay, so let's go ahead and start to implement this algorithm that we talked through here. Now, we know this is a divide and conquer algorithm, which means we want it to be recursive. Now, recursive functions need 2 things. What 2 things do recursive functions need? It needs a base case and needs a function call. So we need a base case, and then we need a recursive call to our function. Now, how do we know if an array is already sorted? That's our base case, right? If it gives us an array, and we say, we don't need to do any work, and we can give you a sorted version of that array. What does that array look like in this beautiful hypothetical universe? Yeah?
Every number is greater than or less than the number.
We could do something like that. We could say, you give us an array, and before we go on, we're going to iterate over this, and we're going to compare every element to the element before it, and we're going to see if this array is already in order. But I'm really lazy, and that sounds like a lot of work. What's a really simple, what if we could restrict the kind of arrays we get? What would be a simple array to tell if it was sorted or not? Yeah, if it just had 1 element or 0 elements, right? You're totally right. Actually, we might revisit that, because I think that'd be interesting to see what kind of gains we could make in efficiency. So we could actually use what you described as a base case of just do another linear pass and see if it's already in order, which would be really cool and would make it a little bit faster, but it wouldn't necessarily give us any big O runtime efficiency, so we're going to come back to the optimization. That's clever, though. So I'm going to be lazy, though, and pick the easier way of, well, I know if an array is sorted, if the count of the array is less than 2, which means if it's equal to 0 or if the array.count is equal to 1, however you want to represent this in a way that makes sense to you. I think I used guard before. But guard to make sure that the count of the array is greater than 1. And if we have 1 or fewer elements, then that means we're already sorted, so we're just going to return what you gave to us. There's any number of ways you could write that particular conditional. So this one here says, hey, if there isn't, so make sure that the array has more than 1 thing in it before going on. And if there's 1 or fewer things in it, then just return that original array. You give me an array that only has number 7 in it, well, that's a sorted array. We don't need to do any work with that. It's already sorted. You give me an array that's empty, that's already sorted. Don't need to do any work with that to know it's sorted. So that's going to be our base case. Now for a recursive call. We're going to want to do a little bit of work first, because we need to build these 3 arrays here. We need to make our pivot. We need to have our smaller, our greater, and our equal to. Now we're just going to make a simple pivot here and just arbitrarily pick one of the elements in the array. We could just pick the last element. We could pick a middle element. Doesn't really matter. Let's go ahead and just make it the last element. Why is it safe to force unwrap here? Yeah, and we guarded on line 5 to make sure that the array had at least 2 things in it. So we know we have the last thing. So again, you should sparingly be using these here, but I could call this at r dot count -1 or whatever. But because I know that our guard is going to catch any empty arrays, I feel safe enough to go ahead and just force this right here. So we've got our pivot. Now what we want to do is build those 3 separate arrays called smaller. We've got our equal, because remember, we might have duplicates in our array, and we've got bigger. So we build our 3 separate arrays. Now, again, as I mentioned earlier, we are making a lot of arrays in this, so our space is going to be like linear or maybe even quadratic. It's not great for this one here. We could be doing it more efficiently by swapping around a bunch of stuff in place. That algorithm is a little bit tricky and it doesn't help you understand what quicksort means. So we're just going to go ahead and put that by the sideline for now. So we've built these 3 arrays here. What do we do with them? We iterate over our array that we have that has at least 2 things in it. We say for every element in the array, if the element is smaller than the pivot, we should probably be using our isSorted here. This would just be doing smallest to greatest. But let's go ahead and use our sorted closure here. So if our elements and our pivot are in sorted order, what that means is that the element is smaller than the pivot, where smaller is defined by this closure. Could be anything. Smaller could mean like has fewer characters in its name, or has, I don't know, more T's in like a particular string, whatever. Like that's our smaller. Like if they're already in order, if it should be to the left of it. I should call that left, equal, and right. Whatever. So if it is already sorted here, we're going to go ahead and put it in the smaller bucket. Things that should be on the left. So we're going to take our smaller, and we're going to append this element here. If instead those 2 things are equal, the element and the value here, and the pivot, excuse me, then we want to go ahead and put it in that equal bucket. And if it's not sorted with it already, if it's not equal to it, then it has to go in the other bucket that we have left. Go ahead and make these should be vars, not lets. Then we can go ahead and put it in the bigger bucket. So now once this is done, we've built 3 arrays, smaller, equal, and bigger, that'll represent whether the correct bucket for the thing to be going into. So smaller stuff that should be on the left, equal stuff that's equal, bigger stuff that should be on the right. Now that we have our different collections, we can make our recursive call. What we want to return is the application of quicksort to each of these components. So we want to quicksort the smaller array by whatever the isSorted closure is, plus quicksorting the middle array, equal, which we don't really need to quicksort since we know everything in it's already equal, so we don't really need to sort that again. Plus the array of things that are bigger by our isSorted closure. And this will go ahead and sort an array for us. Recursive calls obviously where a bunch of the tricky bits of work are doing, right? But like any recursive thing, you're returning something, and in that return statement, you're doing a bunch of work that's going to put in other return statements and put other stuff on the call string. In this here, using this as an example, we pick our pivot, we then go and make our buckets smaller, equal, and bigger. Then we return whatever array we get after quicksorting this, adding the middle, and then quicksorting this. And that will smash together into our final sorted array. See if it works. And we'll see how long it takes to actually sort something. So let's build a random array. So random R. And our random array will be, let's take 100 elements. We'll map to just get a bunch of random numbers. And int.random from 1 to 1,000. So this is an array of 100 random numbers. And now we want to go ahead and sort it and see if we actually ended up sorting it. So go ahead and print that random array. I will then make a sorted array, which is equal to the application of QuickSort to our random array by this right here. And then I'll go ahead and print the sorted array. So we'll see if we have any interesting bugs in execution or if this is in fact going to be sorting our array here. Oh, we see we got both of our print statements. We see first we have a unsorted array right here, 849, 149, 979, bunch of unsorted stuff. And down here we have a nicely sorted array, 4, 4, 7, 25, 25, 42, 71, handling duplicates, a suspiciously large amount of, as we go into sorting. Now, the neat thing about this here is if we look at how many times we're executing it. Remember for our bubble sort, our insertion sort, for 100 elements, we would have had to do like 100 times 100 things, like 10,000 or so, maybe 5,000 in practice. Here, we only ran this like 300 times, right? We hit each of these buckets here, this 300, this 69, 269. So we didn't actually run it that many times in order to get what we wanted. And if I increase this to say 1,000 elements instead, this would have made our insertion sort take forever spinning around to try to figure out how fast it was. For our quick sort, once it loads, we've still got a bunch of things we need to churn through, but we're still on the same order of magnitude. We had 1,000 things. We only ran this here, maybe, I guess this here, maybe 10,000 times. So we only had to look at everything 10 times. And that's actually pretty much exactly what we got to before when we were looking at the log thing, right? We had 1,000 elements. Log base 2 of 1,000 is about 9. And the rough math right here that we're looking at says we had to look at about 10,000 things, like in those whatever times. Which means for every element, we had to look at it about 10 times. And we had 1,000 elements. That's really good. And that aligns with our understanding of what the runtime should be for this here. And it is much, much faster. For comparison, let's grab our one of our other insertion sort or bubble sort implementations, which is somewhere I assume. And then see about, I'll find a canvas like this. Yeah, let's grab one of our insertion sort or bubble sort implementations and then see how long it takes in virtue of comparison. So we'll benchmark, and then we can also benchmark our own sort against whatever Swift has come up with for theirs. It's binary search. It's a small. Let's grab our bubble sort. That's what the bubble sort in it somewhere, right? And insertion sort, great. So let's grab, and why not insertion sort? Or insertion sorted. All right, let's grab this. So now we've got our insertion sorted as well. I'll slack that out. You saw how I found it, but I'll go ahead and slack that out too now. So I'm just copying here an insertion sort implementation. This is also from our lesson. Just to get a sense of how long does it take to insertion sort something in comparison. So let's do our neat little time benchmarking trick. So we'll go ahead here and do some benchmarking. So let's call start time is equal to a new date object. We make our sorted R, and then here we can go ahead and print quick sorted in, what is that, start date dot subtracting, what was that? Time interval since date, let's go with that. Time interval since start time. Seconds. What's up? Oh, this quicksort stuff here?
Yeah, I got that too now. It should, a similar implementation is also in the lesson, though I might have done it a little bit differently in this year. Hopefully better, but you never know. Great, so this is our quicksort benchmark, and then we're gonna do the same thing. We're actually gonna use the same array, just to make it sure it's fair. So we're gonna take start time 2 is equal to date. And I should call this insertion sort start time is a date. Then insertion sorted R is equal to insertion sorted array of random R by our lesson closure. And then we'll go ahead and this will be our insertion sorted in whatever seconds. And then for fun, let's do the Swift one. So we'll do Swift sort start time is equal to a new date. Let Swift sorted R is equal to, I guess I never actually use this. No, whatever. What's our random R dot sorted. We can see that here. This is the same closure we have. There's happens to be throwing, which we just don't need to care about right now. And then we'll go ahead and see how long it took Swift to do. I have no idea. We'll find out though. I'm excited to see how well we did. It should be here. Okay. So now we've got code here that's building an array of 1,000 elements, and we'll see how long does it take for quicksort to do it, how long does it take for insertion sort to do it, and how long does it take for Swift to be sorting it with whatever it has built in. So I'll move for insertion sort to the top actually. Alright, let's run this and see what it does. So we can see we've got our timestamp. We're now chugging along to be doing a bunch of these inserts here. Okay, so it took 6.6 seconds for our, oh man. So it took 6 seconds for insertion sort. It did take 7 for a quick sort, and then it took about 0.04 for a Swift sort. So why did it take slower for a Swift sort? We did fewer operations in it. But because I think we spent so much time making these arrays, I think that it actually costs us a little bit of runtime, which is kind of interesting. Let's run it again and see if that's replicated. Ready to continue. Yeah, so what we're looking at now is we can see that the Swift sort is still really good. Our insertion sort is still okay. And our quick sort has to spend so much time building each of these arrays that it's actually not gaining us that much time, even though it's doing fewer operations. So how would we fix this? Instead of implementing a sort here that works by building these separate buckets, what we would do is have that fancier partitioning so that instead of breaking out into our smaller, equal, and bigger buckets, we take this original list here, we take our pivot, and we shuffle things around inside of it so that we end up with stuff smaller on one side and stuff bigger on one side. I'll grab an implementation of that. Again, it's not as important that you understand how that partitioning works, but I just want to show that to show the runtime for it. So let's grab Swift's algorithm club quicksort. So Swift Algorithm Club is a great resource. That's a Ray Wunderlich thinger. Now they're actually building theirs the same as us. There's their partitioning. Okay. Alright, so this is so you can see they start the same way we do. They build their pivot, they then take their less, their equal, their greater, and they just smash them together. The next bit they do, which I'll just grab to see if we can get the gains we want to, is this neat little partitioning algorithm here. And you can look over this here. I'll post this link inside Slack as well. So the partitioning here is what lets you go ahead and shuffle things around without actually needing to build these separate arrays. I'm not going to cover this here since it's a little in the weeds, but I'm just going to steal their implementation to see if this gives us the runtime that we're looking for. So I'm going to grab this QuickSort Lomuto, which is the particular partitioning algorithm that they're using, and then grab the actual partition that they built here, which is partition Lomuto. So theirs happens to be in out. That's fine. So we'll go ahead and switch our QuickSort to be this implementation here. That's in the link I just shared out. And that'll be QuickSort Lomuto. You have to call it with the smallest and biggest in there, right? Alright, fine. So we'll go ahead here. We'll switch our quick-sorted. So right here, we'll just go ahead and sort this random R copy that we'll make. Random R is equal to random R copy, and then we'll go ahead and call our low part. What's it called? QuickSort Lomuto. QuickSort Lomuto, passing in the random R copy. The low, this is for the partitioning. You have to be playing around with the different indexes that you're trapping. We need to have our little ampersand to show that theirs is in out. And then our high is going to be the count minus 1, I believe. Random R copy dot count 1. Okay, so now what we've done is we've just stolen an implementation of QuickSort that doesn't spend all this time building bulky arrays and instead does it in place. Hopefully theirs is faster. If not, we'll figure it out. That's very interesting. Still slightly slower. It might be, so the conclusion I have to come to now is because these arrays are so randomly sorted, I think we might be picking bad partitions for them. Or it's just taking longer to have them run. I'm actually very curious. So let's go back to ours. Let's figure out if it's a number of operations that's longer and we're picking bad pivots, or if it just takes a while to be churning through the amount of operations we need to be doing. Yeah. So random should be better. Lomuto is not actually the most efficient. There's another one that's a little bit better. Yeah, that one's a little bit better. This is actually interesting. So let's take our quick sorted. Let's go ahead and just print like how many times we have to look at it. Well, no. So we want to see like how many times does our quick sort end up running. You know, we saw that the amount of times that we were actually looking through was about right. I think that what's hurting us is that it just takes a while to be like looking at each of the things rather than we're actually doing the wrong number of operations. I believe what we're looking at right now is actually what the... All right, let's try to get a little clever. Once we have, let's try to copy what I think Swift does, which is if we have an array with 10 things, let's try insertion sorting it. Let's see if that makes it better. If that doesn't work, I'm just going to throw my hands up and say, believe me, it's better. We saw the amount of operations. But I want to try that first. All right, so now if we have, we're going to change our base case. Try to, so this is what you're talking about before. Can we be a little smarter with our base case? Let's see. So if we have 10 elements, instead of returning the array, we're going to return an insertion version, an insertion sorted version of the array. So this is still our base case that's going to work, but it should be more interesting. Let's find out. So let's go back to this here, and let's use our sorted array. And let's see if this is let's see if we actually get a time efficiency from this here. I have no idea. I'd like to say the answer would be yes, but We'll find out. It might be slower, but it's worth trying. Yeah, okay, fine. Worth a shot, though. So, in any case, QuickSort is still going to be taking fewer operations, but there looks like there's something a little bit wonky in how much time it's taking to go through it. So I'm going to chalk that up to like a interesting peculiarity to how we're building like these arrays here and how the partitioning was working. Yeah.
The point of linear division operation is not that they're faster,
Mhm.
it's scale better.
Yes.
Is 1,000 a small number in this case? If you did 10,000, would you start to see performance?
That is a good question. So or good comment rather, is that 1,000 isn't really that many elements as we're talking about scale. So maybe if we have 10,000 elements instead, that will give us enough data to tell us whether or not we've actually built something that scales better. So let's take a look at that. Yeah.
Ben, you mentioned earlier that the candidate is usually a long array.
Mm-hmm.
How come in our function it's the last one?
Well, they're all random, so it's not going to make a difference. Yeah, it's a good question, though. The middle pivot thing is, I think actually the Lomuto partitioning actually picks the end for the pivot. It doesn't really matter unless you have information about how the array is organized.
Okay.
Right, so if you knew, for example, that your array was kind of sorted, right, like let's say you have a collection of names that aren't totally random, but it's kind of sorted, then the middle is going to be a better place to be looking at for information rather than the end, right? If you have no information at all, then any element is just as good as any other element. Yeah. So we've let this be chugging for a little bit, and I think we're still spitting through our like insertion sorting here. So this is clearly going to take at least, well, if it took 9 seconds for 1,000 elements, it's going to take a very, very long time for this many here. So let's go ahead and just try our quick sort against 10,000 and see if we're fast enough to find it. That's a real test here. So now we're seeing insertion sort couldn't hack with 10,000 elements. 10,000 times 10,000 is in the 7 figures range or something. So let's figure out if our how long it takes our quicksort to be running here with these 10,000 elements. So we expect the amount of operations that we have here to be somewhere in between 10 and 20,000, give or take, because the amount of times that we have to look at everything here should be relative to how many cuts in half that we have to make. So if we have 10,000 elements, how many powers of 2 do we need to go down in order to get down to the base? While this is chugging, the arithmetic on that says that we'll need to look at, where's our on base 2 of 10,000. So I don't know off the top of my head, unfortunately. Would that I did. So this is telling us there are 13. Now keep in mind, when we had 1,000, it was 9, I think. So even though we increased the amount of stuff in our array by a factor of 10, we only increased the number of things we had to look at by 4. So logarithmic stuff scales very, very slowly in comparison to linear scaling, which is what makes it such a great runtime in terms of performance efficiency. So let's check back and see how our algorithm is chugging along. So we're at, well, I guess if we have 10,000 things, and we're saying we'll have to look at everything 13 times, then that means that the sum total of all of these things is going to need to, on average, be at about 100,000 or so before we actually end up stopping. What's that? Plus 70? Yeah, give or take. So like somewhere in that order of magnitude there. So we can see that we get there, but it still seems like the implementation that we built here maybe is working a little slower than we want to in terms of like actual operational time. But importantly, I'll just wrap on this. So this is a big, all this whatever about like runtime here
actually doesn't speak to what big O notation is actually measuring. If we've built something that scales, and I can tell you how many times it's going to run before finishing, and the answer is this will take 100,000 operations to finish. Even if each of the operations takes longer, it's still a more efficient runtime than something that takes shorter but takes 1 million operations to do. The reason for that is any individual operation can get faster or slower. Like, imagine that we had a sleep statement here where we were just doing like thread.sleep for like a second. Its big O would still be better. Even though it would take longer to run with that thread.sleep in it than maybe a worth performing algorithm, it still would have a better big O in terms of its runtime. This is it. So this, I guess, really highlights that you can't always do your like runtime comparison and know what the efficiency of an algorithm is. So perhaps unintended point, but an interesting one with this. From both of the algorithms, both ours and the one that we grabbed from the Ray Wonderlic, it actually took a little bit longer or the same as insertion sort. That doesn't mean it's a less efficient algorithm. What it means is that the individual operations that we're doing take more time. That doesn't mean the algorithm is less efficient. It just means it might actually take longer relative to the scale you're looking at. Now, it is absolutely true, however, that as long as that time is constant and doesn't scale with the number of elements, there is a point at which we'll have enough elements so that this algorithm here would happen in a faster amount of time. So we can see that we wrapped up. It took a little bit of time. Don't get me wrong. It took 255 seconds to actually sort this with QuickSort. However, we had to get up to what? So I said that number was about. That's about right. Right. So we knew how many operations it would take. I write here that this was roughly the scale we were looking at, and we saw that we had 57K, 55K, and 8K, which is roughly in this order of magnitude, right? So we did a pretty good job of understanding how many things we would look at. And that's really what big O notation is doing, is it's telling you how many things are you going to need to look at. We have 10,000 things in our array. We're going to have to look at everything 13 times. So about on average, we're going to have to look at 130,000 things, give or take. With insertion sort, if we put this one back in the mix and run this here, we have 10,000 things. We know that insertion sort, on average, is going to need to go across n and down n, which means that the number we'll have to reach will be 10,000 times 10,000, which will be a 1 followed by 8 zeros, right? 2, 3, 4, 5, 6, 7, 8. So the number that we're going to need to reach is 100 million right here. That's a lot, that's a much bigger number. So your point before is exactly correct. 10,000 is certainly big enough for us to see a efficiency in enough to see a improvement in how much time it takes for our algorithm. So again, it's not about base time, it's about scaling. We took 255 seconds for our QuickSort implementation, which again, it's not great, about 4 or 5 minutes, but we did it. In order for this to finish, this number that's at 5,000 needs to get up to 100 million. That would take a lot longer than 5 minutes, right? Even if it was yes, you can imagine some super quick algorithms that are spinning and doing it quickly, but if we added another 0 then, this thing here, it took 5 minutes before, adding another 0 to our inputs here would probably only make this go to maybe 16 or 17, and would increase this from like 100,000 to 200,000. So instead of 5 minutes, it would take 10 minutes. But if we increased another 0 here, we had 2 more zeros here. And that goes from looking at 100,000 things, or 100 million things, to 10 billion things. And instead of waiting, I don't know how long would this take to get to 10 million? Like days or months maybe, right? In order to wait for it to get to 10 billion, we might not be dead by the time it gets to 10 billion, right? So the important thing to remember with Big O is that it's all about scaling. That as we, looking here to see
what number of operations we're going to need to be running for it, we can predict, and we know how long roughly it's going to take, now that we have an understanding of the runtime of our algorithm, and like how much time it actually takes for my machine to be running it. I know that 10,000 operations, or 100,000 operations, takes about 5 minutes on my machine, give or take. So if I say, well, going from 100,000 to 200,000 operations will mean that I'll have to take 10 minutes instead of 5. But we got to increase this by a factor of 10 for how many things we can sort. And it's still doable. Doing the same 10-fold increase for our insertion sort means that we're going from 10 million, or 10 million things to 10 billion things. And that's going to take a lot longer than another 5 minutes to be going through and figuring out there. So we didn't end up writing an algorithm that took a very short amount of time for small amounts of data, but it did finish for 10,000 elements, right? We ended up getting to a solution here, and insertion sort would not have gotten there within that time period. So we could wait for another, day, another week, and this still wouldn't finish these 10,000 elements, and it would never finish the 100,000 elements because it scales too slowly. So, not quite the punchline I was hoping for, but hopefully one that was interesting for understanding what the distinction is between how long it takes something to be running and scaling. So there's, yeah. Oh, yeah, I think so. Yeah, it probably did. Did it take the same amount of time? No, this is awful. I guess it's the same. Is this insertion sort actually working? That's a real question. That'd be funny if it wasn't. Oh, it's because the numbers have so many duplicates in them. That's why insertion sort's getting so good. It's because we're sorting from 1 to 10,000, but we're actually not running into that many duplicates. So insertion sort is not actually called that many times here. That's interesting. Because we would expect on average that we would have this number here not be 10,000, which is what we started with. Because these numbers are almost all duplicates, right? Yeah, so if we add another a couple zeros to our range here of random numbers, then we don't have a bunch of duplicates anymore, and then this is properly going to take the time we needed. That's kind of funny. So our insertion sort happens to be running like almost like a linear time here, because our range of random numbers was smaller than the range of numbers we were picking from. So what that means is that the array looked like, it had 1,000 ones and 1,000 twos and 1,000 threes and 1,000 fours and 1,000 fives. Insertion sort is actually pretty quick when it has so many duplicates. You only need to, because as you're going and doing your division back to be breaking out, there's not that much stuff that has to be moved around. It's much easier to make your different sections when you have so many duplicates in it. So if we expand the range out this way, then we should see insertion sort having some worse performance. Very interesting. Or it's not working, one of the two. But all of this is combined into the sense of runtime is complicated. There's a lot of factors that are impacting it. Yeah, I guess I can actually tell about it. Yeah. So the most important thing from anything about any of this runtime stuff is to be conversant in understanding what's happening when things are running, right? What does it mean? If I said you have a linear arithmetic algorithm here, this process we went through here, you have 10,000 elements and you have to do 100,000 operations or whatever. If we're scaling to 100,000 elements, and we're a linear arithmetic algorithm, how many operations would we expect? Those are the kinds of questions that having more fluency around will help you in the context of understanding what scaling means, and in the context of a whiteboarding interview, how long it'll take to be running your particular algorithms. So we would expect, on average, this insertion sort to not be going to 10,000, which got very lucky at, but instead to be going to 100,000, or 10 million, or whatever that is. A little bit better, but something that's much higher than just a linear algorithm. Goodness. Lots of complex factors going on with these sorting shenanigans here. So anyhow, so my expectation now is that now that we've got fully random stuff in our array and that it's not all duplicates, that this is going to take properly much longer to actually be sorting. Because we got lucky and that it was basically a linear algorithm before. Now this should go up and keep climbing up higher past 10,000, making its way to whatever that 10,000 times 10,000 benchmark is. About half of that, roughly, is where this number should end up for the number of operations that we need to do. That will take much longer than our QuickSort did. We can watch that count up, but I'm going to believe that that's going to go up to some very high number before stopping. Okay, so important things in summation. What to take away from our understanding here? First and foremost is this picture here for what QuickSort is doing as a implementation. So understand this picture, understand what its runtime means, be able to have memorized that this is linear arithmetic, know that this runtime is worse than linear but better than quadratic. Be able to explain how this actually ends up sorting something, that we're picking a middle from our pivot, a left side and a right side, and then we're splitting in half every time until we end up sorting everything down. So that's generally what our, so that's the first point here, is understand what this image is and be able to explain how this image actually ends up sorting. The second point is understanding more about runtime for algorithms and seeing that what runtime is really talking about is scaling. Being able to predict how many operations will I need to do to complete this algorithm, given an input that's scaling upwards. Linear arithmetic algorithms are very efficient because going from 10,000 to 100,000, instead of looking at 100,000 things, we might look at 200,000. So we increase this by a factor of 10, but only double this. Very efficient. Quadratic algorithms are very inefficient. Because if you increase this by a factor of 10, you end up increasing this by a factor of 100. So very inefficient for quadratic algorithms. And know that that doesn't always reflect to the number of seconds it takes to run something. And you might end up in an interesting spot where you have a linear algorithm that starts off like kind of efficiently and then curves straight up. And you might have a quadratic algorithm that starts here and has a period where first it's better and then gets much worse much more quickly. So this picture here, if you're in this range here, that doesn't mean that this algorithm is more efficient. It just means that you're in a pocket where its inefficiencies at scale haven't been discovered yet. Because as you start hitting this benchmark, you kind of fall off a cliff and start getting more and more and more inefficient. And your linear just keeps on chugging at the same rate that it was working at before. So that's QuickSort. It's a fun algorithm. Alright, so this was longer, at least. So it took longer to do. It took that full 10,000. I don't know why there's only 10,000 here. Whatever. This took longer. It took 255 for the first one. It took 318 for this one. And if we scaled up to 100,000, it would certainly be much longer than would actually be able to accomplish. So look for scale when you're looking at the different algorithms that you're writing for understanding whether or not it's going to be better or worse. Okay, so that's on QuickSort. There is an associated lab with that for some extra practice that has similar stuff to what you've seen before. There is, so that's linked to on Canvas. Same sort of test for it that you've seen. One is just to re-implement it. One is to do it while also ignoring negatives. One is to do it in place. For this one here, this is an opportunity to go more in depth into the Lomuto partitioning and try to understand how these partitionings work. How can we do this in place without creating these extra arrays? And then same thing, do it on linked list for practice. Questions on QuickSort? Other than everything. So, Which one? Really? The test case is wrong? Oh, is that right? Can you make a PR to fix it? All right, cool. All right, wait to pull until he makes a PR to fix that test case, and then you can pull. You can just go into the text file and just create a PR from there. Okay, other questions? Yes. Yeah, please.
Let's say if you
I'll bring up the better one on this one here. Go ahead.
if I were writing some code and I knew that some function there had a capped number of operations.
Yep.
But it might be better to choose a less efficient. If I know.
For sure. Like, practically, if you're writing code and you knew that something would only be executed 1,000 times, and it would never be executed more than 1,000 times, you should optimize for being run 1,000 times. And that might mean writing something that would scale much worse to 100,000 or 1,000,000. And it's rare that the pack would be that big, but it's certainly possible. And you should be writing, now, if you knew it was capped, and you knew that no one would ever change it, go for it. It's rare to be working somewhere and not have somewhere in the back, well, we have 1,000 servers of this right now, but maybe someone's going to ask us, maybe we're going to expand and build things for it. So it's rare that you would want to not be building for scalability, basically. But it could happen. It's really possible. Like if the supply that you're working with is like fixed, you're like, there's like 100 silos of whatever like on the planet, and it would take 50 years for anyone to build another one. You optimize for those 100. So yeah, the Big O cheat sheet is a good graph, by the way, to a good resource to look at for this here, and you can kind of visualize what these runtimes look like. So our quicksort stuff is inside this universe of the the bad range. That's so normative. I think it's okay, but whatever. It's in the range of like influence where you're like, well, you don't grow that quickly, but you grow kind of quicker. Linear is super great. Logarithmic is fantastic, and then quadratic is over in this horrible range. So like that actually is fine. Like quadratic algorithms are really, really bad for like runtime efficiency. Seems good. All right, that's enough yelling about quicksort for now. I'll go ahead and Slack out the link once we've cleaned up that test case for you, and then I'll stick around here to help with any questions that you have on understanding the quicksort stuff. Thank you all.